Okay, so here is our part 3 of section 4.3, and we've got a problem to work on here. So we're given a function, and there are a few things that we need to find. First thing is the intervals on which f is increasing or decreasing. So here's our function f. We want to know where is this function increasing and where is it decreasing, or in other words, where is the derivative positive and where is the derivative negative, right? Because where the derivative is positive, it means the slope of the tangent line is positive. If the slope of that tangent line is positive, it means the function must be increasing. So to get started here, we need to find the derivative, which is negative 6x plus 3x squared. So to find the critical numbers, we set that equal to 0. Looks like we could factor a negative 3x out and get 2 minus x. So if this times this is 0, of course it could mean that this is 0 or this is 0. So of course, in this case, x equals 0. In this case, x equals 2. And at this point, we have our two critical numbers. We're not going to get a critical number where the derivative doesn't exist because the derivative exists everywhere. So then what we do is make our little number line here. And we split it up at 0 and 2. And we pick some test points. So I'll say negative 1, 1, and 3. And then we just need to figure out what the function is, or what the derivative is doing at these points. So I'm going to pick these 3 test points. These are going to be my test points, negative 1, 1, and 3. Again, they can be any numbers in these 3 regions. And we need to see if the derivative is positive or negative on these 3 regions. So I'm going to take the test points and plug them in right here. I'm just going to look here, and all we really need to know is, for instance, when I plug a negative 1 in here and here, we need to know if we're going to get a positive answer or a negative answer. So just looking at negative 1, if I plug a negative 1 in here, I'm going to get a negative 3 times negative 1. That's a positive number. 2 minus minus 1, positive number. So right here, I get a derivative that is positive, which means the function is increasing on this interval. So then I take 1, plug 1 here. That's going to be a negative. Plug 1 here. That's a positive. Negative times positive is negative. So I know on this interval, the derivative is negative. If the derivative of the function is negative, that means the function is decreasing. Then finally, we plug in the 3 here, and I get a negative number. Plug in the 3 here, I get a negative number. 2 minus 3 is negative. So negative times negative is positive, which means that over here, got a positive derivative, which means that the function is increasing. So then we can use our first derivative test, and we look at right here. So we know the derivative is 0 here, so the function itself flattens out here. But before that it's increasing, after that it's decreasing. So the function's increasing, flattens out, then decreases. Increases, flattens out, decreases. So we've got this peak, right? So we know there's an absolute, or there's a local maximum here. So there is a local maximum here, and the local maximum is f of 0, And when you plug a 0 into the original function, not the derivative, the original function, when you plug in a 0 for x, you get 5. So that's the local maximum. And then at 2, looking at what happens at 2, the function is decreasing, then it increases. So it's decreasing, flattens out at 2, then increases. Decreases, flattens out at 2, then increases. So I've got this shape here, right? So there's a minimum there. So we've got a local minimum here. The local minimum is f of 2. When you plug in a 2 into the original function, we get a 1. So to answer part A, part A said find the intervals on which f is increasing or decreasing. So part A, f, the function itself, is increasing on, and then looking over here, it's increasing from negative infinity to 0, and then also from 2 to infinity. So we've got negative infinity to 0, and also 2 to infinity. And f is decreasing on, right here the function is decreasing on this interval from 0 to 2. Decreasing from 0 to 2. And part B says find the local max and local min values. Well, part B, local max, I guess we could just say equals f of 0, which is 5. So really the local maximum is this 5 here. Or what some people do is they write it as a point. So local maximum equals 0, 5. That works. Local min, I guess if you write this as a point, you could say is 2, 1. Or of course you could write it this way too and say f of 2 is 1. But what's important is we need to get the y values here. So local max occurs at 0, 5. Local min occurs at 2, 1. So that takes care of part B. Part C says find the intervals of concavity and the inflection points. And now this is something that we haven't done yet. So for part C, to find the intervals of concavity, let's be consistent here. There we go. To find the intervals of concavity, we need to use the second derivative. So the second derivative, so looking at the first derivative, if I take the derivative of that, we're going to get negative 6 plus 6x, and then we set this equal to 0. So 6x equals 6, or x equals 1. So what this means is this is an x-coordinate of a possible inflection point. We don't know if it's an inflection point yet. So what we have to do is check concavity on each side of this point. So here's 1. So we've got a 1 here. It will be a inflection point if concavity changes from one side to the other. So what we really need to do is pick another test point. So this is going to look sort of like what we did here. We pick another test point. So I'll go with 0 and 2. And it's just a coincidence that 0 and 2 is the same as this 0 and 2. That isn't, normally going to be the case. So with these test points, we want to plug these back in to the second derivative. So when I plug a 0 in here, I'm going to get a negative 6 plus 0. So right here, the second derivative is less than 0, because when I plugged a 0 in here, I get -6. So since the second derivative is less than 0, it's negative. When you're feeling negative, you have a frown, right? So this is concave down, or concave downward. So the curve is concave downward there. So then we plug in the 2 into the second derivative. We get -6 plus 12, which is going to be +6. So here, the second derivative is greater than 0. When the second derivative is positive, just think when you feel positive, you're smiling, concave up like a cup. So the key is that concavity changed here. It changed here. If it didn't, if this is concave down and this is still concave down, then this is not the x-coordinate of an inflection point. But in this case, concavity changed, so this is the x-coordinate of an inflection point. So this means that we've got an inflection point, and it's a point. We have to keep in mind it's a point, so it's got an x-coordinate and a y-coordinate, right? The x-coordinate is 1, and when you plug it into the original function, because it's a point on the original curve, when you plug 1 into the original function, you get a 3 for the y-coordinate. So we do have an inflection point. So for part C, the interval of concavity, for part C, we can say concave up on, looking over here from 1 to infinity. So concave up on 1 to infinity, concave down on, and looking over here where it's concave down, -infinity to 1. -infinity to 1, and I'll just throw this in here too. The inflection point is 1, 3. And then finally part D, they want us to put all this together and sketch this graph. So for part D, let's see, we'll make a XY plane here. Got X and we've got Y. So we've got, let's see, 1, 2, 3. So the things that we know we've got a local minimum at 2, 1, right? At 2, 1. So at 2, 1, there's a local minimum here. So I know it's doing some kind of thing like this here, local minimum. There's a local maximum at 0, 5. So the local maximum here, so it's doing something like this. Got an inflection point at 1, 3. There's an inflection point. So concavity changes here. We also know we're concave up like a cup from 1 to infinity. So from 1 to infinity, we're concave up. So it's going to connect here. So this inflection point will connect to the curve, concave up. And then we are concave down from -infinity to 1. So we're concave down here. So this is going to connect here. So this is going to go something like this. This comes around, does something like this. And as far as we're concerned, this is as much as we need to show. Like you could set the curve equal to 0 to see where this crosses, but this is all we need to show. We're showing we've got the concavity, we've got our local max, we've got our local min, our inflection point is right here. So as far as the graph goes, we just want a basic graph that shows the things that we just found, concavity and local max and local min. So that's pretty much what we'll need. Just going to mention one more thing on this one though. It doesn't ask us to, but just so you can see how the second derivative test works, I'm going to do this one kind of off to the side here. So with the second derivative test, so let's say, let's write it like this, second derivative test. So we've got our second derivative. We found out that was minus 6 plus 6x. So the way you would use this is you would plug in the our two critical numbers. So we had a critical number of 0 and 2. So if I plug in a 0, I'm going to end up getting negative 6. And if I plug in second derivative of 2, we get positive 6. So the way the second derivative test works is this. So we plug in our critical point, we get a negative 6, and the negative 6 is less than 0. So the second derivative test says, since the second derivative is negative, it's negative. If you feel negative, you don't smile, you have a frown, right? So if you have a frown, it means that the curve is doing something like this, which means that the point that you found has to be a local max. So by the second derivative, that means there's a local max here. There's a local max at x equals 0, which is the same thing that we found before. And then also f prime of 2 is 6, which is greater than 0. Second derivative is greater than 0 when second derivative is positive. When you're feeling positive, you have a smile, right? You have concave up, like a cup. So concave up means that there must be a minimum here because it's concave up. So that means there is a local minimum at x equals 2. And of course, to find the local maximum, you just plug in 0 into the curve like we did to get the 5. And to find the minimum, you plug in 2 into the function like we did to get a 1. So 0 goes into the function. I may have said curve, but plug 0 into the function to get the 5. So usually people just use the first derivative test, but this is just to kind of show you the second derivative test also works. So that should get you going on section 4.3. Some of them take a little time, but make sure you put in your time. The optimization problems at the end of chapter 4, they're going to be much easier if you understand everything that's happening in this section. So give it a shot. And if you have any questions, just send me an email. And if I get a bunch of questions about similar problems, I'll do those on a video and put those on Blackboard also. So give it a shot. Let me know if you have any questions.